Welcome back. Let's continue. We move forward from the deep learning to use unsupervised learning. In the previous lecture, we start talking about clustering, and I give you basically two options. Talking about unsupervised learning, talking about clustering. Previous lecture, we review the first algorithm, K-means. I explained to you how that one works in general. Moreover, I mentioned to you the source code for the implementation of that kind of approach. For the implementation, you can do it from scratch. I am not going to ask you to do that. However, I am sharing with you the source code on GitHub. My goal is that you review the source code and be sure that you understand what is happening there. You know Java, you know data structures, so it should be easy to understand, not for you to program, not because we're going to follow with that, just for you to be sure that the process is clear. However, the second approach, the important one, is there are libraries that you can use to implement this in your programs. In particular, in the previous lecture, I showed you one of those libraries. It's a platform. What I show you is a tool that helps you to work with this in a graphical user interface. And we review the idea of, okay, select the algorithm, select the data set, run the algorithm, classify the clusters, and visualize your results in the performance. We stopped with the graphical user interface. Something that I need to review is, okay, but what if I want to do a program and include in my programs this library and therefore put this as part of my software, right? Because that is the goal, to create an application with these things. Moreover, what happens if I want to use clustering, but with another algorithm? There should be something better, hopefully. Now, we need to talk about the API. We need to talk about the library that I mentioned. This is the tool. Hopefully you already have it. And I am sure that you notice that inside of the tool, there is one file with that name, .jar. If you have Windows, probably the file is there in some place. If you have a Mac, you know, you have one big thing, open the content, and inside of that, you have that file. And if not, you can get the file over the internet, in the web page, whatever. But that jar is the library that you need to include in the project in order to be able to run the examples that I am going to show you today and further, right? And you know how to include the jar in your project. So I am not going to explain that part. Good? Okay, everything that you need to work with cluster using this library is to include that jar in your project. Done. Should be something easy. Now, source code. In order to do the simple example, the algorithm that we reviewed in the previous lecture, K-means, if you want to do a program that do what we described, the program is here, by the way, so you can get the program. You don't need to make this from scratch. The program is going to look like this. This is the full program. Now, the important lines, these three. Do you understand what is happening there? And again, you never worked with the library before, maybe, but do you understand the step 1, 2, and 3? Data source, a class in the library. Do you remember that we need some kind of data structure to store our data, to get the data from a file and put the data in the memory, because we need the data in the memory in order to be able to work. That library has a class, data source, that is the closest thing that we have to data set in the previous library. What is the parameter that we pass to the constructor of data source? The file, right? The file. Now, Good news, the library allows you to work with several different formats of files. I am going to talk about it, don't worry, but that one is the file that have the data. Easy. Second, line number 10, what is happening there? Data source. We're going to be able to work with several different types of files. These files are going to have inside a lot of things and the data. A lot of things, header, comments, descriptions, whatever. And the data with the headers and the real rows. The data source is going to store everything, but in some point, the only thing that we need are the rows, these things here. And those rows in this library are called the instances. Instances, notice the plural. It's a new object from a new class, and we get those from our data source. And these instances are the ones that we're going to use to work. In particular, those are the ones that we're going to use to build our model. Our model. Model. How many clusters? Models. The data that you're going to use to create this model. Model. The class. The constructor. All this idea of the algorithm is used to create an object from a class that have inside the methods that you need in order to do that thing that we described before. Make sense? Okay, wait. This is an example of a program in Java in which you want to use this algorithm to do clustering. And according with the explanation that we create in the previous lecture, one parameter that you need here is to specify K, how many clusters you want to create, right? In this example 3, with that data, do it. Help me. What do you think is going to happen later? I am going to show you. If we want to use clustering, but this algorithm, I do not want to use that one. It's not the best one. There are others, right? In particular, if you look to the picture, I think there is something called like this. Well, there is others like this, and there are more. We're going to talk about this too. But what do you think is going to happen or should happen here if, for instance, instead of using this, I want to use this or this? Can we agree with me that the only line that we need to change is the line 11? And the only thing that you need to do is to figure out the new name for one class here, one class here. But by the way, these three are brothers in a hierarchy of classes in which each class implements a particular clustering algorithm. By the way, do we remember the name of a pattern that we use when we want to have this collection of algorithms together? Huh? Strategy 1, 2, 3. The only thing that you do there is to select the one that you want to use. Now, be careful. For this one, you need to specify K, right? That is something that you need to know. Like, okay, the first one, the simple one, I need this parameter K. Okay. Can you imagine that the other two, one of the advantage that they are going to have, hopefully, is that you do not need to specify K. One of the advantages of the other two, hopefully one of them have that advantage in which I do not need to specify how many clusters because I do not have an idea of how many clusters. I really want you, algorithm, to tell me how many clusters you can find. These two are going to be able to do that. Can you tell me another thing that I need to change there in order to use this or this? Line 12, delete. What do you think will happen if I select one of these two in which it is not mandatory to specify how many clusters do I want? I really want the algorithm to decide. However, I keep the line number 12. You're going to force the algorithm to create that number of clusters. They can decide the number of clusters. They have that capability. But if you specify the number, the algorithm is going to follow your lead. Makes sense? However, I am sure that this is not what you want to do. Key means mandatory, the line number 12. For the others, one of the things that you need to be aware is there are lines that you're going to remove, but basically everything else is going to be the same. Good? Now, can I do this? Just print an object. Software engineers is going to call the toString method. What is going to happen is going to print fancy information about the model. If you remember, we did the same for neural networks. And we get information about the neural net, the number of nodes, the connections, and so on. For this, similar thing is going to happen. Clear, right? Okay, good. So that is libraries at the top. Good news, your IDE is going to help you with almost everything. When you use a class, automatically you can check import the library. The only thing is you need to have this .jar that I mentioned before in your project. Otherwise, this is not going to work. Easy, right? Small number of lines, one library, and we're doing clustering, at least with the algorithm number 1. Now, notice the line 9 and the line 10. I create a data source, and from the data source, I extract the instances. This data source in particular is working with a particular file with this particular extension that you are noticing there. Did you know that extension? And hopefully no. Why not? Do you remember that we are using this tool? And do you remember that the tool is from a particular university? The one with the beard there. Okay, they also create this format. They create the format, really. I'm going to show you. But it's a format that they use to represent data sets. And somehow you can search online for data sets in that format, and you're going to find a lot. For instance, you can find the iris data set. Remember that we have these common separate values, the iris data set. You can find the same data set, but in this format. And I am going to show you the format, but the idea is that format is connected with this particular library, with this particular tool. And you can be thinking like, okay, if that is the format that this class data source is expecting, what about if I have a file for my data in something different? Like what if I have common separated values or something that is not supported in the library? Line number 9 and 10 is exactly the same that this box with the white color. And we need instances. Yes, we can create instances, the data from a data source that is from this file, whatever. But also you can create instances using in the constructor as an input a buffer reader with a file reader. And I am sure that you're familiar with these two guys. File reader, buffer reader. The common classes in Java that you use to read text files. As far as you have a text file, and that text file can be read, you can pass that as a parameters for instances. It could be the same guy, the RFF file, or this can be a comma separate values. We don't care. The instances are going to take care of putting the memory, the data. These instances is the class that is equivalent to the one that we reviewed before as records and data set. Makes sense? Okay, I am going to add you to work with RFF files, and I am going to add you to work also with CSV files, comma separate values files. So basically, what you need is this or this, and the rest of the program is going to be as I showed you before. So two lines for loading the data, depending on the files that I give to you. In particular, I am going to add you to work with this data set of the weather, and I am going to add you to work with my data set of grades of my students. Let's see what can we found in the grades. Good? Two things. Good. Now, before you work, the data set, the extension ARFF is basically a file like this. If you open the file, and I am giving you the version of the iris data set in the format RFF. Did you notice what it is? Information above. Literally, you are going to have this add relationship. What is that? The name of the file. Okay. Add attribute. Did you notice the add attribute? The name of the columns and the data type of the column. Numbers. Oh, okay. The class attribute. The label. But we're working with unsupervised learning and we do not have labels. If you have the information in a class column and you can use to evaluate the performance of your unsupervised algorithm. But if you do not have it, that class is not going to exist. Makes sense, right? For the iris data set, you have it. We are going to train clusters, and then you can compare your clusters versus the results that you have it there. After that, add data. And literally, add data and down, you have the data as a comma separated values. 1, 2, 3, 4 numbers, and the class. This can be an enter, 1, 2, 3, 4 numbers on the class, 1, 2, 3, 4 numbers on the class, and so on. Clear? Is the iris data set.
You're considering instances.
The what?
Instances.
What is?
Which of these? Only this part is considered, only under data is considered as instance?
Yeah, only below the data, those are the instances. In fact, this is my PowerPoint. I should have here enters, but from here down, 150 lines, because remember that is data set 150 rows. Each row literally is going to be there. Good. So, worst case scenario, guys. Worst case scenario. If you do not want to work with new classes, or if you do not want to be worried about the format of the information, can you manually transform a file, ARFF, to a CSV? Yeah. Open the file, delete everything above, add data, it's a CSV. Okay, can you transform a CSV to a ARFF? Add some information about the CS file, obviously change the extension, done. And what information should I put? Add data, mandatory. Add relation with a name, something that you can figure out. The hardest part is to create the attributes, the data type, and the classes, the enumeration. Why the enumeration? Because in the data, I have here the names, but remember, the computer is really going to use numbers. So when you create the enumeration, this is 0. So when you do the performance, these are 0, 0, 0, 0, and so on. It's something that is going to happen internally. Obviously, it's something that you need to do manually if you decide to move to CSV, because the process is something that you need to do before, right? Clear. No problem with the formats, hopefully. Okay, this is not machine learning, it's just preprocessing data. Good. So now, this is an example of a data set that is not the Irish. The Irish you remember because you have it before. This one, do we understand this data set here? Or when you read like relationship, attributes, data, we know what is happening. How many columns do I have here? Do I have the class? No class, therefore this data do not have results, but this data have this 1, 2, 3, 4, 5 columns. And the columns, as you can review, there is one, an enumeration, 3 values. Here you have these strings. In the comma separate values version, you need to transform those strings to 0, 1, 2. The second one is a real number. The next one is a real number. The next one is 2 values, Boolean. Again, you can transform to zeros and ones, but here is true, false, true, false, true, false. And the last one also need to be transformed to zeros and ones, but here is yes, no, yes, no. Good? This web page, a lot of data sets in this format. So if you need one, there are some ones there. Good? Files with this format of the data, including the word that later you can need. They are not the only ones. I give you the link to be sure that you have access to some of those files, but Google data sets in this format, and you're going to have a lot of them. In the link that I shared with you before for neural nets, remember that repository of almost 1,000 of data sets? There are some of them in this format. Moreover, some of them in different formats. It is not rocket science. Good. So we have inputs. That is fine. Next, the program that I showed you before, the program that reads the data set and in a couple of lines run the k-means algorithm. The output that you are going to get when you run the program, the output that you can get when you create the model and then print the model could be something like this. Let's see. Do you remember this? This table is exactly the same one that I showed you in the platform graphical user interface, remember? When you run this from the graphical user interface, this is exactly the same output, but in a text array. How many rows my data set for the weather has in total? Number of rows, at least here in these examples that I run. How many clusters the model create with k-means? How many data per cluster? Do you remember that information? That information is like, okay, that is important. The columns, data set averages, centroids, key information for my clusters. Okay, more things there. The cluster, the centroids, the errors. We need to talk about the errors. We need to talk about, okay, this is good or bad. Here, use the information when I run and create the model. The evaluation is something that we need to talk more in detail. But so far, the output hopefully is something that we understand, either with the Explorer, the graphical user interface, or you running your program in source code. Clear? Okay, so the output, the input, the source code. Let's talk about the algorithms. Because I am going to ask you to do clustering, and I give you some data sets. I am going to give you more. And when you're going to run clustering, your first approach probably is going to be to use this one, but we're going to talk about evaluation of performance. And I am sure that you want to have more options than just one. More options. What is the problem with having used one? What is the problem with the one that we already reviewed, K-means? And I am sure that you noticed the problems in the previous lecture. We are searching for a center, and we're connecting some elements with the center just because it's close to that center. But sometimes the fact that I am close to one particular center do not mean that I belong to that cluster. I show you one picture in the previous lecture in which, well, what happens if you have some elements here and other elements here, and this particular guy could be very close to the center of this, and therefore this algorithm is going to connect these guys with this cluster, even though clearly this could be one and this could be another. The distance of the dot sometimes is a good approach, but for some problems could be a very bad approach. That is the reason because we have other options, because some pictures like that one cannot be exactly a good choice to run the K-means. Moreover, a big problem, a huge problem with the K-means is the letter key. We need to define how many clusters. And several times, like for my example with my students, it's like, okay, I want to create clusters of my students according with the grades. How many clusters do I have? I have no idea. I could have the good ones and the bad ones. Two maybe, but that is a guessing approach. So two problems, and those two problems need to be solved by another algorithm. What option do we have? At least I want to review with you two more, these two. Fancy names. The last one, expected maximization. EM. That one. That one is going to work with probabilities, not with distances, not Euclidean distances. That one is going to use likelihood. In particular, log likelihood. We're going to talk about that again. Help me. Neural net. We talk about negative log likelihood. Here, notice, I am talking about likelihood, and I am talking about log, but I am not talking about the negative. Is that an issue? No, the only thing that is going to happen is that here we're going to have numbers that are negative. The only reason because we put negative before is to make numbers positive. Okay, tell me, doesn't matter if I have negative log likelihood or use log likelihood, what is the best value if I use that tool to check for errors? Zero. Make sense? The best case scenario, something that is going to be good if likelihood is zero. Numbers that are negative, more negative, less good. So higher the value, even though the top is going to be zero, the better. Good. This one, using probabilities, using likelihood. We do not need to specify the number of clusters. I am going to talk about this, but basically the algorithm is able to figure out what is the best number of clusters because it's going to be checking the best number that reduces the likelihood. So make the final error the lowest. Another option, DBSCAN. DBSCAN, you notice this name in the picture that I showed you. Hopefully you remember the picture, and at the top, K-means and DBSCAN was also there. It's a famous one, fancy one. The full name is a density-based algorithm. What? Don't worry, we're going to talk about it, but the full name, density-based spatial clustering application. We need to understand what is noise. We need to understand what is density-based, and we already understand what is cluster. Density-based algorithm. DBSCAN. DBSCAN is also going to work with distances, but we need to talk about a different approach for distances. K-means distances, and we measure the error with square error, MSE. DBSCAN, distances, a different way of measuring distances. We need to talk about it, but still we are measuring the error in the same way. EM, we're going to move from distances to probabilities. And because we're going to move to probabilities, we are going to work with likelihood. Remember that we did exactly the same with neural networks. We work with neural network with the sig modes and the error MSE, but then we move to neural network with the softmax and the likelihood and something improved. Same ideas here. Okay. Number one, DBSCAN. Let's see. Imagine that you have a data set in which these are your dots, the small dots. For some reason, the dots are in that way, that is kind of a face. Can you imagine what could happen with a data set like that if you run K-means? It's not going to classify the red, the blue, the green, and the yellow, right? There is no way that K-means create this picture. It's going to put this together, and this together, and this together. And the problem is that the circle around is going to belong to maybe 3 different clusters. Clustering, that kind of data, is a picture. Image recognition. Yes, you can use neural networks, but can you imagine that I can have a picture of this table and basically ask for this picture, apply some filters. We are going to talk about the filters, but that was something that we did with neural networks. And after applying the filters, all this table here is going to disappear. This is going to be kind of a black spot, and the chairs are going to be like 2 gray spots. Just one picture. And then you can imagine what is going to happen if we apply clustering, and this can be one cluster, another cluster, and another cluster. I can recognize that there is an object here and 2 objects there. A car, a camera, looking to the street, 1 person, another car, a tree. Yeah, you can apply neural nets, very fancy, and recognize things, but also filter, black and white, put together pixels. And this is a cluster, that is a cluster, and a different cluster. I do not know what they are, but I know that there is an object there, here. And later you can apply a neural net with this particular cluster to know if this cluster is a person, a car, or something else. But the first work is clustering things that I need to care about. Makes sense? Okay, in that scenario, I would like to keep this circle as one cluster because I would like to think that that circle, that data, is probably the border of the table, and inside there are other objects, or at the top there are other objects. So I want to consider the red one cluster, and the others small clusters. K-means do not help me with that. What can I do? How I can modify the K-means in order to be able to do something like this. And moreover, remember, I do not want to tell you how many clusters do I have or how many clusters do I want. I only want you to tell me how many you can find. Good? What do we do? Well, step number one, imagine that I have data here and here and here. DBSCAN. You are not going to tell me how many clusters do I have. So by default, step number one, I am going to think about one cluster. Okay, one cluster. What is the center for that cluster? Random. We are learning, right? Okay, only one and random. Random. It should be one of the dots that I already have. It's not going to be a random here because there are no data there. It's random one of the rows. Random one of the rows. Good. Let's start here. Now, search for the dots that are close to you. Can you find at least one dot that is close to this one? That one. Yeah, I am sure that you can find this one. Put that one in the same box that you are, because you are going to become a cluster. Good. Next, repeat the action with you, but also with your new friend. Search for dots that are close to you, are close to your friend. Okay, close. What does it mean to be close? You need to define a particular distance that satisfies the threshold of being close. So I am looking for some other element close to me. Here. Okay, we are a cluster. Next, I am going to search for more elements close to me. Nothing. Okay, you. Elements close to him. Okay. We three are a cluster. Okay, close to me. No, nothing. Okay, close to him. Him. We are a cluster. Again, close to me. No, close to him. Done. Okay, close to him and to him. And this is going to move. This is going to move. And it's going to be this and this. And all these guys become a cluster. When I am going to stop? When I do not have any other element close to me. Close how? You define a threshold, a distance. When there is no possibility of new connections, we are a cluster. If I was here, that is going to end in this space here. Because basically, I start everything randomly because I was here, and all you guys are close enough to be considered one cluster. So cluster number one here, and I cannot connect with you because the distance here is too big. So You are not part of this cluster. Okay, what do I do next? I am done. I cannot move anymore with this one. A loop. Do you have more elements? Yes. Repeat the same. Randomly select another point. Randomly select another point. Let's select randomly this guy. Randomly, right? Randomly, I am going to be here. Okay, can I find someone that is close to me? There? And again, it's like, no, too far. No, too far. Okay, I am alone. I am. Remember the name? This density, with noise. What does it mean, noise? That not all the rows are going to be part of one cluster. There are going to be rows that do not belong to any of the clusters that I am creating. And notice the difference with k-means. K-means everyone belongs to one cluster. With DBSCAN, this guy here is alone, cannot be connected with at least another one. This guy here is not a cluster, do not belong to any cluster. The label for me is null. I am not part of the clusters. I am noise in the data, an outlier. Makes sense? Okay. And then what I do? Repeat, select another random element. Another random element. Obviously, all the elements that I already use here or the noise, somehow I am taking care that, okay, I already busy, so I am not going to use you anymore. Another random, maybe the other random is going to put me there. And then I am going to search for the close elements, and I am going to start growing, and I am going to create a cluster. And when I cannot find anyone else close to me or any of the members of my team, I am going to stop, and I am just going to have another cluster and another cluster. And hopefully you will notice that when I select one of the guys in the circle, I am going to start growing, and this is going to start growing, and all of them are close. All of them, even though they are a circle, they are going to be put in the same group, in the same team. There are going to be a lot of noise, a lot of dots that are not close enough to any of them. They are going to be there without a label, without being part of a group. No predictions for them. That is fine. Clusters, noise, done. My new algorithm. If I ask you to implement k-means from scratch, moreover, if I give you the implementation of k-means in Java, can you imagine what kind of modifications do you need to do in order to move from k-means to DBSCAN? Don't worry, I am not going to ask you to do it, but just asking, can you imagine the kind of modification, how to program the thing that I just explained? You need to add some loops, right? Yes.
How to identify N and E in that case?
Sorry, again?
How to identify N and E in that case?
N and E, okay, parameters, mostly. In this case, number one, you do not ask for a particular number of clusters. It's just going to happen that you are going to start with one, and then you are going to grow. And then you have two parameters or two numbers that you need to take care of. I mentioned the following. I mentioned that I start with one dot, and then I am searching for a particular distance from me to another one. Okay, that particular distance have a name, and I use here E. The distance from me to the other. For a program, a parameter. it's a number that you need to specify. There are ways in which you can figure out a value for E reviewing your data. I am not going to go in that detail. It's just one parameter, one number that you need to decide. Second, I mentioned that you need to find another element. I just mentioned that I am here and I just found another element that is close enough to me. And I just mentioned randomly, oh, we are a cluster. Let's define a number n that is how many elements do I need to find close to me in order to become a cluster? Because something that you can define is, okay, we are together here, but no one else. Okay, we two together are one new cluster, or we two together are just noise together. So what is the minimum number of elements together? Okay, we here, okay, we are 6. This is enough for a cluster, or is you 6 noisy points here? Another parameter that you can define. And again, there are ways, mathematical ways, to figure out good values for n and e in terms of reviewing your data. But for you in a program, for the library, 2 parameters that if you want, you can specify. If not, there are values there that are going to run. The library is going to take care of calculating good values for this. Good values, not perfect values. There are always research for this. Makes sense. 2 values that you need. You can change or you can play with the defaults. Good. Okay, so, okay, Nancy, fancy way to do clustering. What about the source code? This is going to be 50% the same as the source code for the k-means. Did you notice that the only thing that is changing is a little bit about the distance, a little bit about another 2 loops in order to find these themes, maybe a data structure to keep track of the nodes that are inside of a particular bag? Source code. Open source. You can go to that address and the implementation of DBSCAN is part of the Apache Commons. It's a class, small class. I mentioned before this, I put the implementation of the k-means in GitHub. You can have it. This one, you can go to this other link there. You can have it. And you can notice everything that we explain here in words, source code, data structures. They are very good examples for you to practice your knowledge of data structures, hash maps, and other things. Anyway, I don't care about this implementation for scratch. What I care is about the implementation in the library. Implementation in the library. Do you remember that the only thing that we need to change in our program was that line 11? And do you remember the name of the class for k-means? It's like we can use this simple k-means. For some reason, they do not want to call it k-means because that class have childs. So there is simple. The simple one is the one that we use. DBSCAN. Do you remember the this idea of density, right? And all the letters. A density-based cluster? Yes, because this is just one example of an algorithm that is density-based. It's just one example of a DB algorithm. Is the only one? So far, you can remember. There is always something to change and improve in any algorithm. And you remember the gradient descendant, the nested, the Adam, Nadam, and continue. DBSCAN is used. Think about algorithm like the strategy. Down, you have k-means and a family. You have this density algorithm and a family and one of the childs. DBSCAN, one class, and you can notice, hopefully I remove, yes, the number of clusters. I do not specify the number of clusters. I just create my model, my object, pass the data as a parameter, and done. Clear? Good. So now we know how to do k-means, and now we also know how to do another one. Next. 1, 2, the other. The other. A loop. Let's see. What if, instead of talking about distances, what if we start talking about probabilities? What is the probability of two dots being a cluster? The probability with this node, that node, that node, that node. Let's create probabilities of rows to belong to a particular cluster. And if we move to that level, something that we need is a function that calculates that probability. A function that is the relationship of what data I am and my probability to be in a particular cluster, right? Functions. Do we have an idea of some kind of function that can help me to move to probabilities? Okay, I really don't care. I do not. The only thing that I care is there is a function that can give me that value. And there are several different options. And each option can be better or worse for different things. The only thing that I care is if there is going to be a probability to belong to one cluster, and there is going to be another probability to belong to another cluster or to another's, what I need to compare is the two probabilities that involve me, and I am going to belong to the one that is the better. Okay, the only thing that I need to know is how to compare probabilities. Because it's not like the higher number or the lowest number, right? There is something else. And what is that something else? Likelihood. Likelihood. And in particular, log likelihood. Help me. Likelihood is to compare two probabilities. Why we introduce the idea of the log to the likelihood? One reason. What?
Simplification of derivatives.
Simplification. More specifically, why simplification?
For the derivatives.
Let me put this in this way. That is correct. Likelihood is about multiplication, right? When we talk about probabilities and the probability of something to happen is the multiplication of something multiplied by something, multiplied by something, multiplied by something. There are multiplication there. Again, I am not going to go into your statistic classes, but there are multiplications involved. What happens when you calculate the logarithm of the multiplication of functions? Because remember, we're talking about multiplying the functions that give me the probability of me belonging to something. So you have function multiplied by function, multiplying by function, multiplying by function. When you get the logarithm of this multiplication of functions, what is going to happen? Multiplication become, and therefore that is simple, that the multiplication, simple, small numbers. That is the only reason, because we talk about log likelihood, simplification of things. And if we go to neural nets, this negative log likelihood is to handle positive numbers instead of negative numbers. Here are going to be negative numbers. We don't care. Clear? Okay. Guys, this one, with that idea, similar to the previous one, we start with one cluster. One cluster, we calculate probabilities. According with the probabilities, we put each element in a cluster. In this case, if we start with one, basically, some of you are going to be inside of that one, and others are going to be outside. And then we check that we have an error, the likelihood. And then we move to 2 clusters. And some of you are going to be in one cluster, some of you are going to be in the other cluster. And we calculate again the likelihood. And we're going to notice, oh, improve or not. It's better to have these 2 or it was better to have the 1? Hopefully improve. And then we're going to calculate 3 clusters, and we're going to put each of you according with your probability in one of the 3 clusters, and we're going to compare, okay, this likelihood improve compared with 2 clusters, yes or no? If yes, we're going to do the same again and again and again and again. And in some point, having n plus 1 clusters is going to be not as good as having n clusters. And therefore, that n clusters is going to be the answer for our problem. Start with 1, create, stop in the point in which the things do not improve. How do I know that do not improve? Because I am going to use log likelihood, work with probabilities. The way that I put you in one particular cluster is according with probabilities. I am not going to go into the details of the statistics, but you have functions to, for each data row, calculate probabilities of belonging to something. EM. This is the idea. Now, did you notice that we're talking about good and bad, good and bad, good and bad? Is create 1 and check if that one is good match. Create 2, check if that is good match. 3, check if that is working. And the question that you could have is like, wait, this is the first time in which you are creating 1, 2, 3, 4, but each step you are doing some kind of evaluation, some kind of testing. And the question is like, wait, what I give you is a training data set, but you are telling me that part of the training is to do testing, right? How do you do that? I give you a data set. Can you use this data set, the training one, also for evaluation? And it's like, yes. How? Another fancy word, cross-validation. What is cross-validation? We are the data set. We are each of us one row. Let's do the following. Here, this row is going to be for testing. So let's do the training with all the rows except this one. And then we can use this one for testing. Okay, that is the first time. The second time, because remember, we're doing this several times to compare. The next time, same data set. Let's use the second row for the testing, all the others for the training. I am not using the same row for testing always. Cross-validation, my data set, and I am moving the testing in the data set. Again, that is happening inside while this guy is running. For you to have these numbers to compare, for you to have the idea of whether or not you need more clusters or you can stop with the ones that you have. Probabilities, log likelihood, density with the DB, or use distance in Euclidean distance with k-means. 3 options. Good news, you do not need to implement this from scratch. It's already there. Now, for the picture, this idea of the probabilities in terms of data is going to look more like this. Again, you're going to start with 1. And when you start with 1, all the data is there. And then you're going to move to 2. And the data is going to be like, okay, I am here. My probabilities of having guys inside of me is going to create something like, okay, these groups. The probabilities are going to change the next time according with this comparison that we're doing. It's going to move. And hopefully you get a good result. The circles, the probabilities of being there is going to adjust, and that is going to change which data is going to belong to you. Picture, picture, picture. This is the one that is more unclear in terms of I am not telling you how to measure beyond probabilities, but the code. This is the algorithm. Did you notice my line 11? Oh, good news. This one is used the same name. This one should have 2 words instead of 2 letters. But when you develop a library, please think about the developers, right? Anyway, you create the algorithm and everything else is exactly the same, even though I talk about probabilities and likelihood and la, 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 la. It's happening inside of the black box. You do not care. Well, you don't care except because of the following. Think about your data. You're going to have the grades of my students. The decision that you need to take is you're going to use k-means, you are going to use density, you are going to use EM. Which of the 3 options could work for grades? Okay, you are going to have a picture, data that represent literally black dots in a picture that you apply some filters to move from this to black and white to maybe this, and this, like 3 big black dots there. The picture in black and white, the grade of my students. Which one could work with k-means or DBSCAN or EM, and why? This is the same question that you had before with neural nets. Because with neural nets, you decide to use sigmod or softmax. And if you remember, the decision was about, okay, we want to use probabilities or we want to use the raw data. When we move to probabilities are important, softmax. Here, when your data work better with probabilities, when you want to use probabilities, you move to IM, right? Question, which one could work with probabilities better? The black and white picture or the grade of my students? Pictures. How do you know about it? The dots in the picture, the numbers itself do not mean anything. The only thing that you want is the probability of them to be together, to be one object, and therefore later to identify that object. What about the grades of my students? They are real data. The integers numbers there, or floating point numbers, really represent information, represent your grade in an exam, in a quiz or something. For my grades, for your grades, what you want to measure is really the distance between 2 students using as a reference your grades. And for that, k-means or density are better options than probabilities. Again, if the data represents something, if the numbers are really something that speak for the raw, like grades, you do not need to move to probabilities. I am not telling you that it's something bad to do it. I am telling you, you do not need it because the distance between the numbers itself is telling you something. It's something that you can use to compare. What I am telling you is, in a picture, really, the values of the dots do not represent anything. You don't care about this 255 or 128 that is a gray color or a black color. You are using that data just to put some probabilities of that to be together in a picture, to be an object in an image. Probabilities, EM in clustering, probabilities, softmax in neural networks, values. The numbers are important. You have other options. Clear? Now, the idea is that you play with this, but use a big picture. Now, easy. Next. Right now, I can give you my two data sets, one for the weather and another with the grade of my students. And I can ask you, can you do clustering with k-means? Can you do clustering with DBSCAN? Can you do clustering with IM? And you can do it. Right? Okay, the next question that I am going to ask you is, can you compare which one was better? We need to talk about comparison, right? And comparison, if you only review how many clusters was created, it could happen that the k-means create 3 clusters and the other create 2 and the other create 5. For the Irish data set, you have the correct result, so you can figure out which one is better or which one is close to be good. But for the other data set, including the grades of my students, probably you do not have a correct answer. Because again, I am not using the letters of the grades as something that you want to predict. You have already the equation. I want to know the groups that I have, right? If I have the good ones, the bad ones, and there are something else in the middle, like the good ones, but the good ones that need tutoring, the bad ones that do not come to the class, but the bad ones that need some kind of help. So 4 clusters, not only 2. Comparison, evaluation of the clusters. For evaluation, two things. The library is going to give you a cluster evaluation class. Do you remember the evaluation class in the neural nets? Now you have a cluster evaluation class in this new library. That class is the one that you can use to do your evaluations. Now, what do we need? What do you think is going to be the input for this object from the class cluster evaluation? What do we need to provide as a parameter to do the evaluation? Doesn't matter what was the algorithm that we use. Data, testing data. That could make sense. Okay, can I use the same data that I passed before for training now for evaluation? You can, yes. Be aware that your evaluation is not going to be exactly fair. It's probably going to be very, very good. Again, you can do it. It's going to work. You can do it. It's going to work. It's a good idea. Most of the time, not always, but most of the time, it's not a good idea. Most of the time is data for training, data for evaluation or testing. And we already talked about it. You did the same with neural nets, right? So data as an input here is going to be something that you need. What else? Nothing else. Now, okay, you calculate some clusters, right? You calculate some clusters and you have the centers of those clusters, so the equivalent in the different algorithms. And now you have data that you want to use to check if your clusters are okay. Let me be clear. This is unsupervised learning. So you do not have the correct result. So you cannot tell me, like before, the accuracy, the precision, the F1 score, the confusion metric, because you do not have the data, theoretically. Well, you can do it with the Irish data set because you can run your clusters and compare with the result that you have, but now you need to create this confusion metric and you can calculate the things. But by default, what we're talking here, the understanding is we do not have the correct result. This is not supervised. Okay, what can we really test here? The only thing that I can do is I have my clusters, I have new data, and I am going to calculate for each of my new data, which is the cluster that corresponds to them, right? option 1. In the option 1, I create 1, 2, 3 clusters, obviously because I have data there. In another option with another algorithm, or maybe with the same one, I have no idea. I create an option B, and in my option B, I have 4 clusters, and my 4 clusters, because it's not the best draw, but here I put this as a noise, and here I create another, like using some of them. Makes sense? I have random data. I want to check which of two is better. Random data, one guy, the guy is here. Random data, the same guy, but with my option A and my option B. What I am going to do is to calculate which is the cluster for that guy. Which is the cluster for that guy? Maybe, just maybe, in this model, that one is going to tell me, well, the closest cluster that you have could be this one. Again, could be. Here, maybe it's going to tell me, and let me put this to make more explicit connections. Here and here. What option is better for that guy in blue? This or this? The only thing that you have to answer is the distance from this to the cluster, either to the center or just to the periphery of the cluster. The distance to the cluster or to the center of the cluster, a distance, right? We are going to consider the following. For each of the new elements that I am trying to classify, I am going to take the element, I am going to check the cluster for that element, and I am going to calculate this distance. I am going to calculate the error. That measure, that distance, the error, or how far this guy is from one of the clusters that I create. And I am going to have this 1, and maybe I am going to have a 2, and I am going to have a 3, and I am going to have this 4. I am going to use exactly the same. The only thing that we are going to do is to add the errors of every element that you use here and there. If you add the distance, the theory is that the number that this is smaller is better than the other option. Why? Because most of the data got into a point in which they were close to a particular cluster that you create before. And this close means that they belong to that cluster. And if you have numbers that are big, the addition of the numbers is a big number. That means that those clusters do not really represent the data. That the clusters that you create do not really match with the users that are arriving. Distance. Forget about the distance. We are doing evaluation. What we are going to use for evaluation of clusters, this idea of how good or bad you match with one of the clusters, is not the distance to the centers. It's not the distance to any particular place. The likelihood of this new element to be put in a cluster. And the addition that we're going to do is the additions of the likelihood. Okay, forget the likelihood, the log likelihood. And what is going to happen is greater the number is not really going to be greater. It's negative. Tell me, what is the best case scenario for the log likelihood? You tell me before. There is any way in which 0 is going to be the result of these distances of the new elements and the clusters that I have. And if you think about it, 0 is the best case scenario, because that basically means that every single one of the new elements, the one that I am using for training, is not only inside of the cluster, but is inside, very close to the element that represent either the center of the cluster, or the probability for that cluster, or the density for that cluster is there inside. Getting 0, really, the only way is if you use the same training data for the testing. If you use the same data, you can get the 0. But in a different scenario, it's going to be a number close to that, but not exactly that, 0.0 something. That could be a good thing to get. If you get something like -1, -2, -7, -10, negative, it's not a good cluster. Makes sense? Okay, Professor, do we need to calculate the log likelihood for this? Because I do not remember how to calculate likelihood. The log I remember, but the likelihood is kind of a summatory. Programming, libraries, software engineers, the only thing that you need to know is the correct library. And we did an object for the cluster evaluation class, right? The object cluster evaluation class. We need more data, right? Another data source, another file. Usually you can separate the files. If you do not separate the files, you can always separate in the memory. We can review that later. In this example, 2 files, training and testing. 2 files, because that is what you are going to get in the website that I shared with you. Getting the rows and the object evaluation, set the model that you created before, and set the data for the testing. 2 things. You give that to the object, and then get the results as a string, and you can print it. Or you can just ask for one thing, one number, the number that we're talking about. If that last number is 0, perfect. It's not going to be, but you can print the numbers for different models. The one that is close to 0, that is the one that is performing better. But I am sure that you want to review the full list of results. Clear? Okay, guys, no homework yet, but please review the source code and be sure that you can run these programs, moreover, to understand what is happening. Good? See you next lecture. Thank you.